Thanks, everyone. So today I will be presenting the work that we've been doing at the Corrosion Center in Australia in collaboration with the UGent. I would like to thank Tom and Lisa. Everyone knows Tom's and everyone knows Lisa. And the idea of this project was basically to evaluate the performance of 316L, a material that in this case we produce by direct energy deposition, and basically compare it against the rod counterpart, both anneal and cold drawn. Long story short, we found that the DED material had a better performance than the when we compare against the anneal and cold drawn, and let's see why. There was two main stages in this work. One is to evaluate the performance in terms of hydrogen embrittlement, and then try to understand a bit more through microstructure, permeation, and TDS. So those are the main three techniques. Again, the application mainly before under CP. So here we're doing charging by electrochemistry, cathodic polarization. Then we have the permeation and TDS that I will explain through the presentation. Those are the three materials. Let's see if this works. Yep. We have the DED, in which we took samples in the build-up and also in the horizontal direction. And then we have the cold drawn and anneal. There are some difference in the chemical composition, although the three of them were graded as 316L. Hopefully thinking that they would be austenitic, spoiler alert. When it comes to the characterization, both for mechanically and also the hydrogen embrittlement part, we had smooth specimens to do the mechanical characterization. Then we have the notch samples to have the baseline for the step load in tensile test, and three of the samples also with notch for the samples tested in the environment. So let's jump into the mechanical characterization. The main idea here was to analyze, okay, if we want to replace the rod with the DED, which condition should we aiming to replace? And where we observed is that the DED got closer results to anneal than the cold drawn. And then those are the results for the samples tested in notch. Again, the idea here is not only to see the performance for the mechanical part, but also to establish the baseline for step load in tensile test. And we observed that the results for the DED got even closer to the anneal than the cold drawn. So if we want to replace anneal parts, if we want to replace materials printed by DED, we should be aiming for anneal, right, for the direct comparison. So those are basically a picture of the setup. We have our solution. In this case, was a 3.5 weight sodium chloride, normal solution. And we did potential static charging on -105. This is a room temperature. And this is a brief description of the step load in tensile test with an example using the vertical. After we characterize the mechanical characterization in air, with the notch sample, we obtain the fracture load. And then with the fracture load and the hardness, we get the profile. Joshua was speaking a bit about this on Tuesday, but basically what we have is a profile of load with increments. Each increment is 5%. And then if we do 20 steps, that means that we reach the 100% of the fracture load, and therefore the material is not susceptible to hydrogen embrittlement. Therefore, if the material performs less steps, that means the material is more prone to these failure mechanisms. And the first 10 steps, that is the first 50% of the fracture load, is with a holding time of 2 hours. And then for the second one, just to allow a bit of diffusion, the holding time is 4 hours. There are two main reasons why we took this approach. One is that there's no effect, as it was mentioned before, there's no effect on the strain rate. And the other benefit that you can obtain with this is a threshold load in which you don't have any problem assimilated. any effect of hydrogen on your material. This is preliminary data, and in the presentation, we just use this as a screening. But the idea is to keep performing tests so we can evaluate what is that threshold load. So jumping into the results, that's a cauldron. The material did 17 steps, and it was very consistent. When we compare against the anneal, it was ranging from 14 to 16 steps. And now when we plot the DD vertical and horizontal, material reached or completed 18 steps. So in the next slide, I'm going to present the hydrogen embrittlement index, but you can see here that although the presentation is a bit of a clickbait, because I mentioned that the DD had a better performance than the cauldron and the anneal, we need to also consider that the load at which the cauldron reaches is much higher. So for the purpose of this presentation, we are using the hydrogen embrittlement index, but actually we should just at this moment compare again the DED and the cauldron as they have the same baseline based on previous talk this morning. So the idea is to understand a bit why we have that major difference between the DED and the anneal. And as having a material background, the idea is to, I don't know, find something exciting about the diffusion, the trapping, but the spoiler alert is quite simple, and it was mentioned in this symposium before. So the idea was to understand a bit more how the microstructure has an evolution through the testing. And what we started doing was interrupted step loading tensile test. So basically, instead of letting your sample to fracture, we start the profile of the load, and then at a given step, we stop the loading, we empty the chamber, we took out the sample, and we did a cross-section of the material. We start with the anneal. The anneal, as we can see, it doesn't look very good. It has major secondary cracks. We can also see some recrystallization, some twinings, but the main thing here is the phase map. We can see major bands of BCC, which we think that is martensite. This is a research in progress. We still need to conclude to do better, further analysis. And we can also see some straining along those BCC bands. So that was step 14. And then we take it to step 15. We can see some void formation in front of the secondary cracks. We can also see those martensitic bands. And when we take a look of the fracture sample, again, each of these are different samples, of course. Not only we see those bands on the bulk, but also we see, as this is a midplane, this is the only region that is close to the notch. And we can see the presence of BCC phase. Now, what happened when we go to the cauldron? We have less secondary cracking. We have some twinning, some grain recrystallization. But when it comes to martensite content, we don't see much. We don't know if that's mixed index or not, but at least it doesn't look like the anneal condition. We see straining as well. But when we take it to the fracture, when we do a step, we see some more martensite, but it's evident we take it to the fracture level. That was cauldron. What happened with the 3D printed, the additive manufactured ones? This is the vertical one. We see secondary cracking, but we don't see any formation of martensite. And even at fracture, we don't see any formation of martensite. And for the horizontal, we see some red zones, but I would say that this is a misindexation, because when we take a look of the fracture, we did not observe any. So that's basically the maps of the different conditions, the different samples. And what we are plotting here is the MD30. So basically, when the idea is at what temperature, when we apply 30% of true strain, we have 50% of transformation from austenite to martensite. So in other words, how stable is the austenitic phase? The higher the temperature, the less stable austenite is. And this is based on chemical composition. So what we can observe is the anneal and cold drawn, in those situations, in the rod condition, due to chemistry at least, we can see that austenite was less stabilized. So it was more prone to transform into martensite. So then the idea was to move forward to the thermal absorption spectroscopy, tricky samples, because this is 316, the idea is to saturate. We were working at 80 degrees, and here the thickness is 70 microns. And we need to get kind of in a parallel condition, so it took a bit of time. But there is one problem here that when we think about is 20 millimeter diameter, 70 microns thickness, so there's a lot of area, not too much volume. So when we did the charging, we started charging galvanostatically because we need to charge many samples. And then the profile were not good. So the reproducibility of the charging was not good. So at that time we were charging at -2 milliamps. That was around -105 volts, but there was a massive drift on the potential. So then we start doing potential static charging. This is just as a technical note. And we improved the desorption, the ppm rate. But then when we actually analyze the difference in the material, there is not much. All the peaks are very aligned. Again, this is research in progress. We need to get more data. But so far, what we can observe from the activation energies is just purely diffusion. There's no other peaks. We tried extending the temperature range, but there's nothing there. So far, it's not really something about absorption, desorption. And then we obtain also the diffusion coefficients. And then the idea was to compare the diffusion coefficient with permeation data. Again, tricky. We work at 80 degrees, sodium chloride in the charging, sodium hydroxide in the reading. We obtain, so far the data that we have collected was only for DED. And then when we compare against the TDS data, the results in terms of diffusion were pretty close. 4 to the -15, this is square meters seconds, I didn't put it there. That was for the TDS, and when we go to the permeation, it ranged from 5 to 7.5, so quite in the order, but we still need to get the data from the anneal and cold drawn. But again, we don't expect much. It's quite frustrating. So the takeaways. So when we compare the DED against the rod counterpart, we saw a better performance of the direct energy deposition ADT manufactured samples. And we can link it with the phase so far. The presence of martensitic phase on the rod counterpart is well established that it's not good for hydrogen embrittlement. But then it goes down to chemistry. It's not much exciting. And then when it comes to the TDS, we observe similar results. So based on those results, absorption, desorption, we cannot pin that difference in the hydrogen embrittlement performance. And as a technical side note, we think that because as we're charging for 4 days at 80 degrees, and we have a lot of surface compared to the volume, we improve the results by potential static charging. Then for future work, we would like to get those threshold values and complete the experimental matrix. We'd like to acknowledge the support from Woodside and Chevron, University of Kent, and thank you for your attention.